Let's go. Yeah. Lecture 19. I will start by solving a question that uses the formulas that we went over last time. In the last class, I was showing a lot of proofs, and therefore I didn't have time to do any examples. So here's the example question that was at the end of the handout. So you have data of 6 pairs, and the various sums are computed as follows. And with this, you have to find the r squared, r. You have to use the row test to determine whether x and y are correlated at 0.05 significance level, and then find the confidence interval for B1, right? Okay, so let me show you all the formulas we've went over. Yeah, a lot of stuff, right?
We did that just last time.
Yeah, and actually, I actually proved this one, right? I proved these and this. I did a lot of proofs. So if you follow the lecture, then you can kind of gain some understanding of how these formulas came about.
Did you post the last lecture?
Yes, I did. Yeah. So the video is on my channel. So if you missed it, please watch it. Okay, but all we have to do now is to figure out which formulas to use. So let's do one by one. Okay. So first of all, find r squared, r, and the linear regression. And actually, that's a really big problem because here's the formula for SSxy, but this one already requires SSxy and SSx and SXy, which in turn are related with this. So what we need to do is to start out by following these, computing these formulas. Okay. And then let's see how we can use this. So can you see the above condition and what to replace sigma y squared by? What should I replace this one by?
3088.
3088. Okay. You just have to look closely and spot the correct number. Okay. Yeah.
So you're just
I guess.
plugging in.
Huh?
You're just plugging in a sense the numbers.
Yeah. You are. Yeah. You're just plugging in. Yeah. Yeah. So you have to be actively looking at the given numbers and spot the things that you have to plug in. Okay. So sigma y. What should I replace this one by?
112.
Yes. Good.
Hell yeah.
And how about n? 6, right? Okay. So that's what we have to do with a calculator. Let's see, 3088 minus 112 squared divided by 6. Enter. And I get 997.33. Okay. And now you do the same thing for SSx. Okay. And at this point, I advise you to try to go ahead of me. Try putting these into the calculator. So sigma of x squared is 57. Sigma x is, oh, sorry, that's not right. Sigma x squared is 663. And sigma x is 57. Again, divided by 6. Okay. So let's try that again. 663 minus 57 squared divided by 6. 1 to 1.5. Okay. All right, now let's figure this out. Okay, sigma xy, what did I replace this one by? 1400. And these are individually 57 and 112, and divided by 6. Okay. All right, so that was 1400 minus 57 times 112, and then divided by 6. 336. Okay, so we got these numbers. Now, can you calculate small r?
Yeah.
What do you do?
R equals SSxy.
Which is 336, right? We're using this formula right here, right? Divided by square root of the 99, no, actually 121.5 times 997.33. Okay, so that's what you have to calculate.
So in a question, we'll be given like supposed data n equals 6 pairs x.
Right.
That'd be
So,
the
in the question, you'll be given these summations, and the purpose of this is to see if you know how these values R and B1 and B0 are calculated, because if I don't have such a question, then all you would learn in this class is just punching in the raw data into the calculator, and you don't have any idea where these numbers come from. Okay.
What is B1 and B0?
B0 and B1 are the what I used to call in the last lecture A plus BX, A and B in the linear regression. Yeah, I'll explain, okay? All right. So 121.5 times 997.33, enter, and then I get 0.96523. 0.96523. Okay, is that high correlation?
Yeah.
High correlation, right? Okay.
How do you know? It's close to 1.
Well, it's close to 1, right? Okay. It all depends on the data size, because we only have 6 pairs of data, so degrees of freedom is 6 minus 2, so it's just 4. So in that case, to be significant, you really need a high number, but I'm pretty sure this is really high. It's close to 1, so it's good enough, okay? All right, so now what do? We have to now calculate the r squared.
Are you going to square that?
Yeah, which is the square of the small r squared, right? So you just have to square this. Just square this. And that's 0.9316. Or 93.16%. Just a minute, did I round it right? Oh, I should have said 7. Okay, so what does this mean? What does r square value of 93.17% mean? Do you remember what it means?
Like a high correlation?
Hmm?
Is it the correlation?
No. Yes, yes. So how much?
How close your actual points are to your predicted?
No, no. This is saying that the variation of the y, 93.17% of the variation of y is explained by the regression line. So if you forgot what we did in last lecture, the definition of r squared was sum of squares of the residual. No, sum of squares of the Yes, sum of squares of the not the residual, sorry, but the regression. Sum of square of regression divided by the sum of squares of the y. So the sum of squares of y, well, divided by the sample size will give you the variance of y, right? And sum of squares of regression divided by the sample size will give you the variance of the regression line. And it's saying that the 93.17% of the variance of y is actually due to uh, the variance of the regression line. And see, the variance of y is the sum of the variance from the regression plus the sum of the variance of the error. Another name for the error is the residual. So it breaks up like this nicely. So you can, if this value is pretty big, then you can say that, oh, regression is doing a good job in explaining uh, the, the, the variance of y. Okay? Yes. The question was, does that mean the linear regression is 0.9317? No, that does not mean what I said. 93.17%, you have to listen to me carefully. It means that 93.17% of the variance of the data is explained by the regression line. Just from the fact that the data follows the regression, you can kind of estimate that the variance of the y has to be that much. Okay, and 93% of it is explained by that. What's your question? I haven't found a linear regression yet. Okay. Okay. So now what do? We now have to find B1, right? So, I promise I'm going to explain what B0 and B1 mean. So linear regression equation, I've been talking about linear regression as A plus BX, right? But because we're going to be going over to the multiple linear regression. Multiple linear regression uses a lot more variables, so it's actually easier for us to use indices, although I know you hate indices. That's why I didn't use indices before. So instead of using A and B, I'm going to use, instead of A, I'm going to use B0. And I'm going to use B1 for this one. Okay, it's just another name, okay? It's just more complicated name, okay? So it's like, instead of calling a person Bill, you have to call him William. It's like the name has changed to something harder. Okay. Hopefully you don't complain. Okay. So that's our regression, and that means we have to find B1 and B2. Let's think about the B1 first. What is B1? B1 is SSxy divided by SSx. So we have 336 divided by 121.5. Okay. And that one is, where's a calculator? All right. So for that one, we need 336 divided by 121.5, 2.7654, or 2.765. Okay. And now we have to find the B0, which is sum of y divided by n minus B1, the value that we just found, times sum of x divided by n. So we're going to use this formula here to get the B0. So we're going to say B0 is sum of y, which is 112 divided by 6, minus 2.765 times sum of x, which is 57, and then you divide it by 6. Okay? So let's put that in. So 112 divided by 6, and then minus 2.765 times 57, and then divided by 6. You get negative 7.6. Okay, since we've done a lot of calculation here, let me.
Wait, where did the y value come from?
Where did what come from?
The 1112 divided by 6.
Where did 112 come from?
Yeah.
Sum of y is 112 right here. Okay. So I'm just using this formula, replacing the sum of y and sum of x and n and b1. Okay. You just have to keep hunting for the numbers, okay?
So then for B0, what's the equation that we use? Is it the whole y?
So for B0, in some contexts, you may have already given to you the average of x and average of y. In that case, you use this formula. But in this question, I don't see x bar and y bar given to me. So you use this, which is basically the same thing. Even if you're just given this, you should know to use this one because, what's the average of y? You add up all the y values and divide it by n, right? We're given the sum of the y values, which is 112, and now you divide it by 6, and that gives you the average of y. So you see how these two formulas are related? They're basically the same thing, okay? So, maybe I could make it tricky so that in the formula sheet, I will only give you this one or that one. You should know how to use the other one, okay?
I think it's tricky to test.
Okay. All right, so let's delete the other stuff that's not part of the answer. I'll just, yep, what was it? Okay. And then into this linear regression, we have to plug in these values. So this will make it as y hat equals to negative 7.6 plus 2.765 x. Now, it's very important that you write your answer like this. When you're looking for linear regression, the values are not the answer. You need to write the linear regression equation itself. Okay? So this should be your answer. Okay, that's just part A. Okay. Now you have to go to part B. Right. Let's move on to part B. You're still writing? Okay. All right. Now, for the part B, you need to do the row test. And to do the row test, you need to calculate the test statistic. And you will be given this test statistic for the row test. So test statistic for the row test is this. T equals to R over square root of 1 minus R squared divided by n minus 2. Okay, so that's the test statistic for row test. Let me copy this, and this belongs to the next slide. So let me cut this now. Let's put it right here. Okay, so we need to do the test statistics, compute the test statistics, and then use that to find out the significance of this, all right? So let's try this. Our R value was 0.96523. So in our case, this will be, let's see, 0.96523. Here is 0.96523. And what should I go for, use for n? 6, okay? And let's compute this. 0.96523 divided by, and then you need a square root, parenthesis, 1 minus 0.96523 squared. Then, should be this. Oh, messed up there. Okay. And then you divide this by 4. 6 minus 2 is 4. So I'm just going to put 4 and close the parenthesis. Enter. I get 7.3850, which is pretty high. 7. What was the value? 7.3850. Okay, so at this stage, you can go by 2 ways. One way is to look for the T critical at 4 degrees of freedom. Remember, in the linear regression, you need 4 degrees of freedom. So you have to find the T critical from 4 degrees of freedom at 5% significance level using the T table. Yeah. Or, oh, just a minute. Okay, I'll just stick to this one. Yes, you have a question? Okay. All right, so you have this, and then, or you can just use the T distribution to find the, you can use TCDF to find what this p-value is. So if I put 7.3850, and the degrees of freedom for us is 4, 6 minus 2 is 4. If we paste it, we see that 0.9991 is the area left of it, so the actual p-value is 1 minus the above answer, which is 0.000896. So TCDF of 7.3850, comma, degrees of freedom equals to 4 gives you, actually, we have to do 1 minus, and that gives you 0.0008, what was the value? 896.
With your degrees of freedom in this test,
What did you say?
with the degrees of freedom here, why are you subtracting 2?
So the question was, why do you subtract 2 for the degrees of freedom here? You have to do it because linear regression has two constants, B0 and B1. So when that's fixed, you lose 2 degrees of freedom. So anytime you use up something from your sample, you end up losing some degrees of freedom. So when you try to calculate the correlation, you're trying to use these regression line which relies on B0 and B1, and having that just decreases the degrees of freedom by 2. Do you have any other questions? All right. So since this is less than the significance level, the we see that x and y are correlated. Or to be more formal, you should really say the null hypothesis is that they're not correlated at all. And we reject the null hypothesis and conclude that there is significant data to show that x and y are correlated.
Okay.
Yes,
What's the significance level?
significance level is 0.05. Yeah. I mean, it differs from problem to problem. If it's not given, just keep it as 0.05. Okay. Yes. Oh, because so the question was, why do you do 1 minus? Well, if you do TCDF, what does this TCDF do? It draws the bell curve, and it captures the area from negative infinity up till that given point, right? But you're doing. Oh, just a minute. Oh, in fact, that you should always do the two-tail test. Actually, I forgot about that. So you have to times 2. But that's still less than 0.005. Okay. All right. So see, you're always doing two-tail test for the row test if you convert it to t. And because it's two-tail, you need the right tail and the left tail. So what you have to do is you have to subtract from 1 to find the right tail, and you have to times 2 to get the total area of the tail. I feel like we've done this enough times that you should know. Yes?
How did you use the significance level in from?
So this p-value, this is our p-value. If p-value is less than the significance level, then we reject the null hypothesis, right? Yeah. Yes. Yes. You compare it. If the p-value is less than significance level, then we reject the null hypothesis. You have a question?
Yeah, I was just gonna ask if it's larger than the significance level, do we reject the alternative hypothesis?
No. If the p-value is larger than the significance level, then we fail to reject the null hypothesis. That's different than rejecting the alternative hypothesis. Yeah. So we kind of went over that before the second exam. So you probably know the difference between the two. Saying that we failed to prove that the null hypothesis is false is not the same thing as saying that we proved that the null hypothesis is true. Okay. All right. Now let's move on to part C. So here it says find the confidence interval for B1, and what this question is asking is the following. So here's our linear regression, but this is just from the sample, right? And we don't know what will happen if we add more data. Okay. If we have hands on the entire data of the population, then this will look somewhat different, right? So even these values, negative 7.6 and 2.765, those are values that we're just guessing from the sample, and therefore they come with some confidence interval. So that means the true B1, and I think some textbooks would use beta 1, because we use Greek letters for the population value, right? And we use the Roman letters for values obtained from the sample. So if we are aiming for the true beta 1, then it will be 2.765 plus or minus some error, right? Some error. But how do you get that error? Well, it's this one. That's the error, okay? So we first have to figure out the standard deviation of B, which is this formula right here. But then that's also same as this one, divided by SSx. So let's write it like this. We know that we're going for SB, which is this, which is, well, the top part is same as this one. Okay, so let's put these in there. Okay, but that's still, we still have to find SSE. Okay. All right. So how do we find SSE? Okay. So there are many ways, but I guess this looks simple enough, right? So let's first find out SSR. I'm just doing backtracking here. I really want to know this one. But to know this, I need SB. But to know this, I need SC. But to know this, I need SSE. But to know this, I need to know SSR. So you see how this reasoning goes? Okay. It's a lot of hunting for the true values, okay? All right, so let's start with SSR. It's B1 times SXY. So let's think about this value, which is 2.765, that's B1, times SXY. What was our value? Was it 336, I think? What was the value? 336, right? So we come back, we have to put 336. And according to the calculator, 2.765 times 336 gives you 929.04. Okay. And then you have to find out SSE, which is SSY minus SSR. But we also have SSY somewhere here, right? SSY is 997.33. Where is it? 997.33 minus 929.04. There are other ways, like for example, since we know 1 minus r squared, since we know the r squared, we can do 1 minus r squared and multiply that by SXY. But that will require more math, which, although the calculation is simpler. If this is the given in the formula sheet, I think this is all you can do, okay? All right, so let's put that into the calculator. 997.33 minus 929.04, enter, 68.29. Now we plug that into SSE. Yes, you have a question?
Why you divide square root of x on the,
What's the question?
why don't you divide it by square root of SSx?
All I'm doing is I'm just plugging into the formula. Right. Do you see it here? Where is it? Here.
But on the SE one, it doesn't have the bottom part.
Yeah, but I need to find SB. Okay, if this is too confusing, just find SC first, okay? SE is what? Square root of SSE, which is 68.29. And then you divide that by 6 minus 2, right? So what's that? 68.29 divided by 4. Oh, quit. No. Okay, second square root. 68.29 and then divided by 4. Okay, so you get 4.13. Is it 4.13? Okay. All right. And then you get SB by dividing the SB equals to dividing the 4.13, the SE, by the square root of SSx, right? But what is SSx? We also have that value previously, right? That's 121.5. So I put that in here. Again, you go to the calculator. 4.13 divided by second square root 121.5. Okay, and you get 0.37468. What is it? 37468. Okay. All right, so that was a longer calculation than I anticipated. I'm sorry. All right, so now what do? Now you have to do T alpha over 2, where alpha is 0.05. So we need to calculate the critical value either from the T table or from the calculator. Since I don't have the table with me, let me just use the calculator. So let's vars inverse T. And the area I want is 1 minus 0.05 divided by 2. 0.05 is our significance level, and you divide it by 2, and then degrees of freedom is 4. So we enter 2.776. Okay, so now you multiply that to the SB that we have, 0.37468. The resulting is 1.04. So this gives you that the T alpha SB is equal to 1.04. And therefore, from all this calculation, you can finally go back and say that this is your confidence interval about the beta one. Okay. So let me put it here. Okay. So that was the calculation. All right. So it looks complicated, but it's just chasing the formulas. You just have to chase down the formulas, appropriate ones, and then figure out which ones to use. All right. So you should try this one. See if you can follow this one without looking at this one, just by using the formulas. Okay. All right. So now our next topic is I want to show you how to get the linear regression done with an Excel spreadsheet. And Excel by default doesn't have the capability of doing linear regression. You have to install an add-in called Analysis Toolpack. Yes?
What if n is like 30 plus? Is there anything different?
If n is
More than 30. There's no.
Oh, okay. So the question was If n is more than 30, do we do anything different? No, you don't have to do anything different. Yeah, you can just stick to the same formulas. You don't have to switch to the normal distribution. Okay. All right. So going back to what I was trying to say is that you need to you need to know how to do linear regression in Excel. And to do it, you first have to install the analysis tool pack. And I already have it installed, but let me, all right, let me just do. Okay, so what you have to do is go into the search bar and type in add-ins, and then you see add-ins right here. If you click that one, then it gives you all these options that you can install for free. There's no need for paying anything. It's just the Excel will install these additional packages for you. So I clicked the very first one, Analysis Tool Pack, and clicked OK, and it installed. And the difference is, what happens is that in the menu, when you click the data, after installing the Analysis Tool Pack, you'll see this thing called Data Analysis. If you don't have the Analysis Tool Pack, this won't appear, okay? So this is what we are going to use today, data analysis. And then once you click it, there are so many different ways to analyze the data. And if you go down, you'll see the regression. And you want to click that one to do linear regression. Now here's a spreadsheet of data of 9 chickens. And it's the data of the weight of the chickens versus the eggs, number of eggs it hatches. So you have the first chicken weighs 7.4 pounds and it laid 23 eggs. And you want to see if having a heavier chicken would mean you get more eggs, which sounds like a good thing, right? So maybe the next time you have a guest and you have to kill one of the chickens to eat, you might go for the lighter chicken because you want more eggs. I don't know when this will be good, but let's say that we want to know that, okay? So when you have such a thing, then you should first think about the independent variable and dependent variable. See, our purpose is to predict the number of eggs hatched from the weight of the chickens, right? So what you do is you take the number of eggs hatched as your Y range, because that's what you want to predict. And for the X range, you want to select the weight. And by the way, when you click these things, you want to click the very beginning of the data, and then you must hit Shift and click the end of the data. Then it selects everything in between. Of course, you can just drag everything here just like that. That's another way to do it, but that's not feasible when your data size is really large. So you really want to learn this. You click the very first data, click Shift, and then while you hold the Shift key, you click the last data, then you can select the X range. Okay. So once you select the Y range and X range, and then you can click all these additional graphs that you want, like residuals, residual plots, standardized results, residuals, line fit plots, and all these things. And then you click OK. And what happens is it's going to do the linear regression and generate this new sheet. And let's see what it produces. So first of all, it will give you the linear regression graph. Let me make it bigger. And you can see what happened was that the actual data are the blue, and the orange one is the straight line, which gives you the predicted value. And it does seem to somewhat follow the regression line, although we don't know how significant it is. And then The difference between the prediction and the true value is what we call the residual, and you can just look at the residual plot itself. Sometimes the residual plot gives you a better idea of how well your regression line is performing in predicting the y value. Now let's move on to what it says. You have the multiple R. This is the R score that we know, the correlation coefficient R value that we calculated. 0.69. It doesn't seem like it's too big. It's not as big as we hoped. The R squared is 47.68%, which means 47.68% of the data, of the variance of the data can be explained by the regression line. And I have yet to explain what adjusted R, but at some point you get this significance, which is 0.057. That's more than the significance level 0.05. So unfortunately, there is no what do you call it? There is not enough proof or not enough evidence to show that there's a correlation between the two things, the weight of the chickens and the number of eggs it hatches. Okay, at the significance level 0.05, we failed to show that. Okay, and you have other things, right? Okay, now let's move to today's new topic, multiple regression. A multiple regression expresses a linear relationship between a dependent variable y and two or more independent variables. The general form of the multiple regression equation is an extension of the linear regression equation, b0 plus b1x, which is, as you can see, you have more than one predictors, right? So you can think of something like house price. Okay, how can you predict the price of a house? Well, there's several factors, but you could look at the square foot of the house, right? Number of bedrooms, number of bathrooms, the close proximity of a nearby railway station. There's some other scale that you use to look at the local high school performance. So like high school graduation rate. So a lot of these things can be factors as x1, x2, x3, x4. And then you feed that in, and if you can predict the value of the house pretty well, that's a pretty good model. In fact, if you ever, well, I guess you guys are too young to buy a house, but if you ever went to websites like Redfin, they would be giving you an estimate of a house that's not even on the market. So you could just click on other houses and they'll tell you what the price of the house was when it was last sold, but also it will tell you according to the current market conditions what the price of the house might be. And those things, if you can provide, it gives you a pretty good idea to the seller and the buyer, and these are pretty important for housing. And you can probably see other cases why this would be pretty important, right? Okay. In predicting some outcome variables, very often there is more than one variable that may influence the outcome. So the thing is, when you plug in all these different factors into the system and make the Excel spreadsheet perform the multiple linear regression, some of them come out as not so significant. Some of them come out as pretty significant. So not only the multiple linear regression enables you to predict the price or the value of y, it can also tell you which ones are the significant predictors. So you might say, oh, okay, well, I thought the number of bedrooms were pretty important, but it looks like it's not that important, and so on and so on. Okay. Now, therefore, when you're doing multiple regression, there are several issues that we want to address. First, how strong is the prediction? Is the prediction pretty strong? Is it like you can explain most of the variation of the y using the linear regression y hat? That's the kind of question. And you should be, once you see that it is really strong, then you have to be able to write down the equation so that you can use it for prediction, right? And then third, you also have to think about which variables contribute over and above the other variables to predict y. So those are the things that you want to know. Okay. So here is an Excel example. Let's see, where's the Excel example? Is it this one? Oh yeah, here. Okay. So here I have a data set of some fish called bream. It's kind of like a bit of a round fish. And they caught, how many are they? 35 breams, and weighted them, measured their length, height, and width, and wanted to see how they are correlated. Okay. They wanted to see whether, knowing the height and width and length, you can figure out its weight or predict its weight. So you can do this multiple linear regression. So let me show you how to do it. So again, go to data analysis. This menu only appears if you have the data analysis tool pack installed. And then you choose regression, okay. And then for the input y range, we want to predict the weight. So we're going to choose the weight here. Click the very first one, hold shift key, click the very last one. So that's your input y range. Now let's go to the x range. Your predictors are length, height, and width, and you have to really click all three columns at once. And that means when you're using this regression, your predictors should be right next to each other. So if your spreadsheet doesn't have the format where the predictors are right next to each other, then you'll have to copy the spreadsheet to another new sheet and move the columns so that the predictors are not right next to each other, okay? So now you have from here, and then, oh, you know what? I just decided I want to do something else. I want to click labels so that the labels come out, right? So I want to start with the weight, which contains the label, and then click this as an input. I want to click label. Same thing for the length, height, and width. So let's do this. No. Okay, and then we will click OK. Let's see. All right, so here's what happened. So we get a bunch of plots, and the multiple R, the R correlation comes out as 0.9705, and that's pretty significant, right? And if you look at this here, the significance is, or the p-value is 3 times 10 to the negative 19. So that's an extremely good p-value. So it's saying that if you use the predictor value as and compare it to true value, it's 94% accurate, 94.2% accurate. Okay, and then you can also see right here that you have the p-value for each of these predictors. And what you see is that the intercept is extremely good at figuring out the weight, but the length and the width are not as good. Their p-value is above 0.05, and it's really the height that is doing the good job. So it seems that of the three kinds of variables, if you want to predict the weight, of course, having all the information, more information will give you more accuracy, yes. But if you were to just quickly figure out the weight without having to measure everything, then all you have to measure is just the height. Okay, right. If you have a fish like this, uh, it's a pretty round fish. This height is all you have to measure, and that can give you a good estimate of how much it would weigh. Okay, so so those are the values. Now you you also have to figure out how to write down the linear regression equation from the value. So in the spreadsheet that I just showed you, the x1 variable was the length, x2 was the height, and x3 was the width. And then these numbers indicate that the weight is predicted by this equation right here. Okay. If you use this equation, then you can predict the weight. Yeah, and I already spoke about the p-value. Now let me talk about some additional items in this table because you do have to know. Now since I can't have an exam that asks for doing Excel spreadsheet during the exam, because you don't have access to computers here, what I'm going to do is I'll be putting the output of the Excel spreadsheet and ask you questions from it. So that means you have to know what each of these items in the output are. Okay, so let's first start with adjusted r squared. So let's go back. So multiple r, that's just it's the correlation coefficient r, but people call it multiple r because this is a multiple linear regression. So it's just multiple r is just r. Okay, r squared we already spoke. It's the square of this value. Now, the first thing that you haven't seen before is this adjusted r squared. What is that? Well, the adjusted r squared is you take the r squared and you have to adjust it slightly because um, here's the problem. If you just add more and more variables, then your r squared just improves. Even if it's just slightly, it will just keep improving if you just start adding more predictors. Because the more data that you have, you're going to have a better idea of what it is, right? But then it's hard to compare two different multiple linear regression. One seems to be doing a much better job than the other, but then you might question whether the reason is just from the fact that you're adding more predictors. So they have this thing called adjusted r squared. You have to multiply by some factor. I forgot to include it in the spreadsheet, so next class I'll show it to you, but that's what it is. So it's slightly scaled down than the r squared. So what happens is that the difference between the r squared and the adjusted r squared will become bigger and bigger if you put more predictors, okay? So yeah. Okay, standard error is just SSE, and you have to divide by some n minus 2 or n minus something. Observations is 35. What does that mean? What does observations 35 mean? Yes?
Is that
N, it's the value of n. Okay, so that's something that you have to know. Observations 35. Okay, now let's look at the regression residual total. Now, regression has 3 degrees of freedom because that's the number of predictors. Okay, we're using x1, x2, x3. And then residual is n minus 1 minus the degrees of freedom. Okay, and if you add them up, you should be getting n minus 1. So let me go back. Oh, and then this mean squared is defined as the sum of squares divided by the degrees of freedom. Okay, so these are pretty important formulas because sometimes from these you have to know the n value. So I might not give you the total spreadsheet. I might only give you a portion of the spreadsheet, and you have to figure out the n value. And so these are very important. And my final remark for today is this ms right here is really this value divided by 3. Okay, this value is this value divided by 31. Okay, so that's how this column is done. And I'll talk about how f is obtained and how this value is obtained in the next class.